Hello everyone, my name is Zhongzhi. Today I'm going to introduce our work called AugViT, Improving Vision Transformer Training by Marrying Attention and Data Augmentation. This work is collaborated with my colleagues Yonggan Fu, Chaojian Li, under the supervision of Dr. Yingyan Selin Lin from ESA lab at Georgia Tech. In recent days, people all observe that vision transformers are pretty powerful and achieve state-of-the-art accuracies across various vision tasks. For example, like image classification, object detection, and panoptic segmentation. And people attribute the success of vision transformer to its unique architecture. Specifically, unlike convolutional neural networks, vision transformers adopt a patch-based image processing pipeline. Specifically, given an image, it first splits into a series of patches, and then they use these patches as tokens and feed it into a sequentially connected transformer blocks. And in each transformer blocks, it features a self-attention module where the patch-wise correlations between each of the input tokens are extracted as a feature of the input image. And the one shown in the red bounding box is the self-attention module. Despite the promising performance of vision transformers, and known question of vision transformer is that it is really hard to effectively train it due to a lack of inductive bias. This is because, unlike convolutional neural network, where the features are locally aggregated in a convolution kernel, this can impose a prior knowledge on the feature that nearby features are generally more related. But in vision transformers, because it computes a patch-wise correlation, so there are no assumptions on feature relationships are imposed to the model architecture. All the relations between the features need to be learned in the training process, which can be pretty challenging. And existing works have already shown that vision transformers need dedicatedly designed data augmentation technique to enable an effective training. Specifically, on ImageNet dataset, using different data augmentations can lead to as high as a 10% accuracy gap. To this end, a question we raise is that whether existing data augmentation techniques are really suitable for training a vision transformer. We categorize the existing data augmentation techniques into two major categories, the image-wise augmentation and the region-wise augmentation, as shown in the figure below. In image-wise augmentation, the perturbation to the image are uniformly added to the image. And in region-wise augmentation, they randomly select a part of the image and apply augmentation on top of it. Although the original augmented image may look fine, but when we consider the patch, there can be some issues. For example, using image-wise augmentation can lead to limited diversity between the patches, as shown in the blue patch here. All of these four patches are just randomly generated, are just some grasses, and it is hard for a vision transformer to learn a diverse between different kind of grasses using only of these two patches. And also, using region-wise augmentation may be too aggressive in terms of the patch-wise augmentation, because it can easily generate a series of patches that are only consist of zero knowledge. To this end, it motivates us to consider whether we can design a vision transformer-based data augmentation technique. Specifically, we want to try to boost vision transformers' achievable accuracy by developing a dedicated augmentation strategies. And in our proposed AugViT framework, we leverage the difference between the convolutional neural networks and the vision transformers to better design a data augmentation framework. Specifically, we consider two major differences, using patches as processing units and the adoption of self-attention modules. Based on each of these two differences, we propose patch awareness into data augmentation, and we also use self-attention scores to guide the augmentation intensities. And here's our major contribution of our proposed AugViT framework. Firstly, we propose AugViT, an input adaptive data augmentation framework to boost vision transformers' achievable task accuracy. Secondly, our proposed AugViT integrates two enablers, a set of patch-aware augmentation techniques, and an attention to intensity mapper. And the experiments have shown that our proposed framework can consistently boost vision transformers' accuracy efficiency trade-off across 2 task and 10 vision transformer models. So first, we will provide an overview of our proposed AugViT framework. The core idea of AugViT is that we leverage the attention map as an indicator to guide the augmentation intensity in each patch. And our high-level insight is that patches with higher attention will be augmented less intensely to preserve their features, which can be helpful for vision transformer training. And the flowchart of our AugViT is that given an input image, we first pass it into the half-tuned vision transformer and extract the attention map and generate the intensity map based on the attention map. Then we use this intensity map to guide the patch-aware augmentation of the input image and finally generate the augmented image by our AugViT framework. And as mentioned before, there are 2 key enablers, patch-aware augmentation techniques and an attention to intensity mapper. In the following, we will introduce each of these 2 enablers. So the first is the patch-aware augmentation techniques. Before we actually go into the detail of our design patch-aware augmentation, the first question or the sanity check we want to raise is that why their patch awareness really affect training. So we do the following experiments that we use 3 different augmentation techniques. The first is the vanilla, which we use the original image-wise color getter. The second is SP, where we use the same augmentation intensity within each patch, meaning that each patch will have the same color getter intensity. And in DP, we use different augmentation within each patch. And the results shows that patch awareness really matters for vision transformer training. By using SP, we can achieve as high as 0.3 higher accuracy over the 2 baselines. So given this motivating observation, next question is that how to augment each patch properly. We also look back to the existing image-wise augmentation, where one of the most widely used augmentation techniques is by changing or manipulating the spatial information using techniques like translation, shear, or rotate. Although this can also be applied to patch-aware augmentation as shown in the red figure here. But we observe that patch-aware augmentation is more sensitive to spatial changes. As shown in the blue and the red patches, some key information or some important relations between features in the object can be sabotaged by drastically changing the spatial information. To this end, our answer to properly design a patch-aware augmentation is that we need to preserve key features in a patch and maintain their inter-patch relations by avoiding the drastic changes in spatial location. To this end, we propose 6 patch-aware augmentation techniques, including patch cutout, patch color getter, patch rotate, and patch grayscale, patch blur, and patch solarization. Equipped with a tool to augment each patch separately, the next question we raise is that how to guide augmentation intensity with the attention map. And we propose a 3-stage solution where we first select a representative attention map, and then we preserve high attention patches, and finally we optimize the attention to intensity mapping to achieve a better accuracy. And for the first attention map selection, we analyze on the attention map generated by vision transformer. As shown in the figure below, using an input image here, we can generate the attention map of all the 12 layers in the vision transformer. And we calculate a row-wise summation of each of these attention map generated. We observe that a certain attention map can better identify the object in the image. Specifically, if we zoom into this attention map and its corresponding row-wise summation, we observe that the high-value patches, where is the more warm color in this figure, correlates well with the location of object. And also, we observe that given different inputs, such kind of attention map also actually appears at the same layer of the vision transformer, showing a strong consistency. To To this end, we adopt this attention map as an indicator of the AugViT because it can tell us where the object is and where the key feature in identifying the presented object. And the second question is that what are the relationship between the augmentation intensity and the attention score? To this end, we also do a simple experiment results on the relation. First, we use following settings. The vanilla is the image-wise augmentation proposed in a SOTA Vision transform-based augmentation. And uniform means that we randomly augment each patch. And the same and the inverse means that we explore different mapping using a higher attention for higher augmentation intensity or higher attention for lower augmentation intensity. The experiment shown below tells us that high attention patches should be preserved to maintain the important feature in identifying the object during vision transform training, because inverse actually achieves 0.2 to 0.5 higher accuracy over the 3 baselines. And last question we have is that, given these high-level insights, how can we design a better mapping function to exploit the AugViT's potential? And the global softmax mapping function comes into our site, where this is the description of the global softmax mapping function, and the G and gamma here are random variable and temperature controlling how drastically we want to change the original distribution. And we also try 2 different settings following the previous slide, where we try whether we should use the high attention for higher intensity or lower intensity. In GS, we have the higher intensity augmentation intensity for higher attention, and inverse GS for a higher augmentation intensity for lower attention. And we observe that the INVGS actually is the optimal setting we have explored, which can achieve 0.1 to 0.6 higher accuracy than existing baselines. And for evaluation, we evaluate our proposed AugViT on 10 models and 2 tasks, including image classification and object detection, which are commonly adopted setting in existing data augmentation frameworks. And we also benchmark AugViT with 2 SOTA ViT dedicated augmentation baselines. And the experiments show that AugViT can consistently improve the accuracy of DIT and the LeViT family of vision transformers. And it's also worth to note that although existing works have tell that efficient convolutional neural network always have a better accuracy efficiency trade-off than efficient vision transformers. But with our proposed AugViT, we can actually boost the performance of the smallest level of efficient vision transformer, which is LeViT 128S, by 0.5 higher accuracy, achieving a comparable accuracy with one of the state-of-the-art efficient convolutional neural network, efficient 9B0, with 21.8% less flops. And on object detection, the superiority of the AugViT also stands, where we can achieve a 0.2 higher AP on average when doing object detection on COCO datasets. And for more results and ablation studies, please feel free to refer to our paper. Okay, and here's my presentation of our work, AugViT. Thank you for your time, and any questions are welcome.